This is problem number 1 on page 97, exercise 11, page 97, number 1. And probably it's going to be relatively easy for us since it's the first problem. I should caution you that some of these can get pretty wicked. Even though we have a way to solve them, we still may run into some pretty rough integrations. So, but anyway, this one I think will be okay. Now, this is not in the format that we need in order to do the integrating factor. So what I need is y prime by itself. So I'm going to divide everything by x, or multiply by 1 over x. And that will give us y prime plus 1 over x y equals to x squared. Now, before we call this p of x. So p of x is 1 over x. And in fact, let me write that. P of x is 1 over x. Q of x, if we're interested, is x squared. Now then, the integrating factor, I, is e to the integral of p of x, 1 over x dx. So we first have to do that little integration, and this, of course, produces a logarithm. So this is e to the natural log of x. And again, we can safely ignore the constant, it turns out. Off the top of my head, I can't explain why, but I would have to investigate it, or you could investigate it. That doesn't make a difference that we need this additive constant. But anyway, let's move on with that. So e to the natural log of x, these are inverse functions, they cancel, absolute value goes. So that's x. The integrating factor is x. Which is kind of funny because when I multiply this equation by the integrating factor, guess what? I get the original problem. Okay, so it's always amused me a bit that I could have just started with the original problem and gone from there. Because now we're back to x y prime plus y equal to x cubed. Alright, so this is the adjusted form from this format. Of course, as you can see, that's what we started off with. Alright, this might be the only problem like that in your book, so that was, I'm sure, a fluke. Now, here's the idea. The left side should be the differential of the integrating factor times y. Okay, so the left side is the differential of the integrating factor. Oops, and the integrating factor is not 1 over x. Sorry about that. The integrating factor is x plus x times y. It's equal to x cubed. Alright, did I say differential? I'm not sure. This is the derivative. The derivative of the integrating factor times y should equal to this left side. Alright, so let's verify that. If I take this derivative, the derivative of x is 1 times y, there's y, plus, because we have a product rule, the derivative of y, y prime, times x, xy prime. So this works. And then if we multiply through by dx, I have differential of x times y is equal to x cubed dx. So this integrating factor idea led to literally a separable differential equation, because on one side my variable is x, and on this side my variable is x times y, the parentheses. So I can integrate this. And when you integrate this differential, you just get this part left over. So I have xy is equal to, integrate this, x to the 4th over 4 plus a constant. Now let's throw that constant in. We'll throw that in. And finally, let me do a little bit of erasing here. If we multiply this equation by 4, just eliminate that pesky fraction there, I end up with 4xy plus x to the 4th. Oops, sorry about that. 4xy equals x to the fourth plus a constant, because 4 times the constant is still a constant. So I'm just renaming my constant. There we go. So this is the solution to our differential equation. And if you wanted to, you could solve for x here pretty easily. Y would be x to the fourth over 4x plus c over 4x. And so you could say, well, y is equal to x cubed over 4 plus c over 4x. If you wanted to divide 4 into c and still get a constant, you could write c over x if you wanted to. So I'm not sure which form the book has. Let's see what they got, how they wrote it. 4xy equals to x to the fourth plus constant. Okay, so this is what the book stuck with. Well, anyway, that's an example introducing our integrating factors, and I'll work a couple more problems here.